On page 496 from Lesson 7.4, I've picked a couple of graphs to help you with as you try to complete this homework assignment. So let's just jump right in and see if we can come up with the graph of this rational function. We'll begin by finding any zeros if they exist. That's another word for saying x-intercepts. Is this graph going to cross the x-axis? So to find that out, we just let the numerator equal 0 and solve for x. If I divide by 4 on both sides, I'm left with x cubed equals 0, and the cube root of both sides gives me x is 0. So I know that this graph is going to cross at the origin. It must cross through the origin, going either from the left approaching downward or from the left approaching upward. We don't know that yet, but we'll figure that out very soon. Okay, and now we'll look for asymptotes, either horizontal, vertical, or slant, or also known as oblique. And so let's go through and see if there are any of those. We'll start with vertical. For vertical asymptotes, those are numbers that would make the denominator 0 if we replaced x with those numbers. And I would always advise you to factor as much as you can. Before you get to this point, it's much easier to find those numbers that make 0 looking at the factored form. So I'm just going to show this original using the factored form of the denominator. All right, and so we can factor this as two linear binomials using the factors of -1 and the back ends of these binomials. So this would be +1 -1. All right, so now I can see that there are two numbers that would make the denominator 0. You can just let each of these equal 0. If you're not sure, take each factor, make it equal 0, solve for x. So one of my vertical asymptotes will be the line x equals 1/2. So here's that line, approximately. All right, and then I'm going to have another vertical asymptote that you can probably tell pretty easily that will be -1, x equals -1. Okay. So let's see, I don't have a horizontal asymptote because the degree of the numerator is larger than the degree of the denominator. But I do have an oblique asymptote because the degree of the numerator is 1 more, and I can't cancel anything between the numerator and the denominator. There are no common factors. So I am going to have an oblique asymptote, and I think I'll just try to squeeze that in here. To find the oblique asymptote, we have to use long division, right? So I'm going to divide the denominator, 2x squared plus x minus 1, into the numerator, 4x cubed. Okay, and so when I divide first term into first term, 2x squared goes into 4x cubed 2x times. And I don't have any, I could put some fillers in here, but I'm just going to leave it like this. Hopefully you can understand if you divide 2x squared into 4x cubed, you get 2x. And now we're going to multiply. 2x times 2x squared is 4x cubed. 2x times x is 2x squared. 2x times -1 is -2x. We always subtract, long division. The x cubes will cancel. So if you want to, you can think of this as 0x squared. So 0 minus 2 is -2x, 2x squared, that's right. And then if you want to, you can think of this as 0x, and 0 minus -2 is +2x. And then we'll continue the process, all right? Divide first term into first term, 2x squared into -2x squared goes -1 times. And -1 times 2x squared, -2x squared, minus x plus 1. And then we subtract. The 2x squares cancel, And we got 2 minus -1, that's 2 plus 1, that's 3x. And 0 minus 1 is -1. Well, at this point, I can't divide anymore because my term that I'm dividing by is larger than the term that I'm dividing into. So this ends up being the equation. I'll make it official and make it an equation of y equals 2x minus 1. Okay, and that's going to be my oblique asymptote. All right, so since you've seen this already, just to create some room, I'm going to erase this, and then I'm going to draw this slant line that's also going to be an asymptote. All right, so let's just get rid of all of this. Not that you would have to erase, but it's going to be a little bit easier for me. Okay, so the line 2x minus 1, this is in slope-intercept form, of course, so it has a y-intercept of -1. It has a slope of +2, so up to right 1, to right 1. I'll go the other way, down to left 1, down to left 1. And I'm going to get my line draw tool ready. And I'm going to make this a dashed line. That's all set. And here is, I'm going to make the color the same. Sorry about that. Okay, down to. All right, here we go. So we have all of our asymptotes. Now one of the reasons why I wanted to pick this problem is it's a little bit unusual. And you'll see that as we get into this middle part between the two vertical asymptotes. All right, so now we're ready to do our table. All right, we've done zeros, we found all the asymptotes. And I should, while I'm in this area, let's just take a look. Always take a look and see if you have any holes. And remember, if you do have a hole, you will have a single number that makes both numerator and denominator 0. Well, that's not happening here because the numbers that make denominator 0 are -1 and +1/2, but neither one of those also make the numerator 0, of course. So we don't have a hole to worry about in this. Okay, so let's start getting an idea of what this looks like, graphing around our asymptotes. So I'm going to start with to the left. You know, you always want to picture it this way. What happens going left of this vertical? What happens between the two verticals? And then what happens to the right of this vertical? So that's what we're going to figure out using our table. Okay, so I'm going to choose an input -2. And I think I'm just going to use the factored form. It's okay if you use the given original form, but I think I'm just going to use this, letting x be replaced with -2. And then down in the bottom, we're going to get 2 times -2, minus 1. Make sure I include that. And then over here, -2 plus 1. Okay, so just using some mental math here, -2 cubed is -8, and -8 times 4 is -32. And then down here we would have -4 minus 1, which is -5. And this would give us -1. And when we multiply the denominators, or the factors in the denominator together, we get 5. So in your calculator, if you want to, you can just do -32 divided by 5, and that should be -6.4. Almost -6.5. So maybe I'll do the regular graph in red. So for -2, we're going to go down 1, 2, 3, 4, 5, 6, and just about 6.5. 3, 4, 5, 6, and a little further. Okay, so now I know that I'm going to have a graph section in this area. And let's just try one more just to get a really good picture. Let's try -1.5. Okay, I'm pretty confident from here. I'm just going to follow this oblique asymptote forever, but does it go a little higher before it goes down? Does it just go down to a point lower? So let's just for being sure, let's do -1.5. And you can go ahead and get your calculator ready. All right, and so in the numerator, when you do this 4 times -1.5 cubed, you should get -13.5. And you could do all this at once. I'm just breaking it up into parts for some who may not be as confident with their calculator. And then down here, this is -3 minus 1, which is -4, times, this would be -1/2. And -4 times -1/2 is 2. So in essence, we're going to be doing -13.5 divided by 2. And that should be, I believe it's -6 3/4. -6.75. Okay, so that's good to know. For -1.5, which is here on the x, I'm going to go 1, 2, 3, 4, 5, 6, and then just a little lower than that previous point. It should be 3/4. All right, so now I know that I'm going to go in this area and I'm going to follow this vertical asymptote forever, going down as y approaches -infinity. Okay, so we got one piece of our graph. Now let's check out where the other pieces. Now remember, vertical asymptotes will be separators for our entire graph. So we're really going to have a graph in 3 sections. We need to know, we've already found out what happens to the left of this vertical. Now we're going to find out what happens in between these 2 verticals. Okay, so let's test some points, some numbers, some inputs in between those 2 vertical lines. We already know that the graph has to go through 0, so that brings up an interesting point. My graph has to pass through this point. All right, so just kind of getting ahead a little bit. If it passes through, typically we say that it should follow a particular asymptote forever. But that's not possible for this horizontal asymptote because it would have to stop here at this vertical asymptote. So this is a rare occurrence. This does not happen very often, but this is one of those times where we're actually going to cross through an asymptote. And that will happen on rare occasions for oblique asymptotes and for horizontal asymptotes. But it will never happen for vertical asymptotes. You will never pass through vertical asymptotes. But as I said, in this particular case, in order to be able to follow along this vertical asymptote forever, I'm going to have to pass through this point, either coming from this side or coming from this side. And now we're about to find out which way it goes. All right, so let me just recap. This is a 0. This is an x-intercept, which means I've got to pass through it. Another thing that's also true is you always follow vertical asymptotes forever, either going up or down. And to make that happen, I'm going to have to cross over this oblique asymptote. Okay, so that's rare that you would not just follow an oblique asymptote, but if I tried to follow this oblique, I'm going to be stopped. I'm not going to be able to go. I'm not going to be able to go forever because I can't cross over this vertical. Okay, vertical asymptotes, it's 100% sure that you will never cross them. You'll never go over them. but there are some rare occasions where you will with oblique and horizontal, and here's one of them. Okay, so let's see. Let's choose a number like -1/2. Let me get my colors back, and we'll just keep doing a table over here. So this will be a table for our middle section, -1/2. So let's grab our calculator again, and we're going to input -0.5 in for x. 2 times -0.5 minus 1, -0.5 plus 1. Okay, so 4 times -1/2 cubed in your calculator. Hopefully, if you're using your calculator and breaking this up into parts, that would be -0.5. Down here in the denominator, you would get 2 times -0.5, which is -1 minus 1, that's -2 times 1/2, and that would give you -1. So we end up with 0.5 or 1/2. Okay, so that's good information. For x is -1/2, f of x is +1/2. All right, so what's going to happen here is I'm going to be following this forever and ever, going upward. I'm going to be approaching that vertical asymptote for f of x headed to positive infinity. All right, I already know that I've got to pass through this point. That's an x-intercept. Okay, and what I'm going to do now is I'm going to test a point to make sure I don't hit this and then go up. Okay, so just for for surety purposes, I've gone through it, but do I go up from there or do I keep going down? So let's just use a number in between 0 and 1/2, and that obvious choice is 1/4 or 0.25. So let's grab our calculator again, and this time we'll input 0.25, and we'll be done with this section. All right. Okay, so to save a little bit of time, hopefully you were able to use your calculator, and when you input 0.25, hopefully you got an output of -0.1, which puts us right just barely below the x-axis. So now we have assurance that we're going to pass through this x-intercept, and we're going to pass through 0.1, 1/4 -0.1, and then we're just going to follow this vertical asymptote as f of x approaches -infinity. Okay, so kind of a unique situation here, passing over an oblique asymptote. 90% of the time, maybe even 95% of the time, you will not have this happen, but in some rare occasions, it does. Okay, so now let's finish this up. What's going to happen in this area? I guess I should have done this in red. Let's trace over it. Okay, so let's just choose an input, +1, and we'll come over here and try to wrap this up. So if we let x be 1, what comes out? All right, so the numerator will just be 4. 1 cubed is 1. 1 times 4 is 4. Here we get 2 minus 1, which is 1. 1 plus 1 is 2. 4 divided by 2 is 2. So for an input 1, I get output 2. 1, 2. All right, and I'm pretty much I know that that's going to be the very bottom. I'm not going to bother with picking a number in between, because this is pretty much a rough sketch. That point is already pretty close to this vertical and this oblique. So that's going to be the rest of the graph. Okay, so that is your complete answer for number 22. Okay, so let's work on this problem number 28, and it's going to be quite a bit different. So, first thing I'm going to do is factor. That's going to make it easier to find my x-intercepts, or zeros. So the factored form of the numerator will be x minus 4 times x plus 2. Board's not cooperating. And then obviously the denominator is prime. So I have this situation where we'll kind of combine a couple of things here. Whenever I've got matching factors between the numerator, or we'd say common factors, that rules out the possibility of having an oblique asymptote. Even though the degree of the numerator is 1 more than the denominator, if there are common factors, we cannot have an oblique asymptote. Alright, so I'm going to go ahead and mark these out, meaning that I only have one x-intercept, or 0, it's called a 0, and that's going to be x is negative 2. Okay, and remember the definition of a whole is a number that makes both numerator and denominator 0. And in this case, we do have that happen. We're going to have a whole in our graph where x equals positive 4. The thing about a whole is I typically wait until I've got something graphed first, and then I'll go back and put a little circle in the graph at this location. But don't forget it. Let's keep that in the back of our mind so that after we have something graphed, we'll go ahead and plug it in. Now that we've canceled, there is no vertical asymptote. And because the original numerator degree is higher than the denominator, we have no vertical or horizontal asymptote. So that takes care of all of the either points or lines of discontinuity. We don't have any lines of discontinuity, but we do have a point of discontinuity. All right, so what started off looking like a pretty confusing function, once we got it into factored form and we canceled where we could, what we're end up doing is we're graphing a line. Y, or f of x, equals x plus 2. So that's why factoring and canceling before you start to actually do the plotting of points is so important. And actually that needs to be done anyway so that you can identify zeros and wholes and that kind of thing. So let's graph the line y equals x plus 2 that has a y-intercept of 2 and a slope of 1. Okay, so you can see how we're going to go through our 0, or x-intercept. All right, and so we'll draw this line, get a running start. I'll make this solid. It's not an intercept, of course, or an asymptote. Okay, so there's the graph of our line. Now I'm going to go back, and I'm supposed to have this line interrupted where x equals 4 on the line. And you might be thinking, well, where would that be? Well, just imagine that you took 4 and you evaluated f of 4. If you input 4, you'd get output 6. So the 0.46 really doesn't, or it shouldn't, exist. If we can't use input 4, then we don't have the 0.46. So the 0.46 needs to be chopped out of this line. And if I could erase, I would. What I would do if I were you is just take your pencil and just mark out that little area representing 4, 6. I can't do that, so I'm just going to put a circle there to basically illustrate that the line travels until it gets to that point, it jumps over that point, and then it continues on forever. And that's the answer for number 28. That one's quite a bit easier than the previous one where we had to do a lot of inputs. Okay, so I hope that helps. You just have, I think, 3 others, and you have one more, I think, that looks a lot like this one. And so do your best, and if you have any questions, let me know.